Tomnomnom, so I'm Tom, that's me. Hello!
No cut.
I'm going to talk to you about a tool that I've been writing a work that I got permission to open source, which is awesome. It's called JSluice. And if you know what a sluice box is, you'll notice that the logo is actually slightly inaccurate. That's a pan, but I'll talk about that in a bit. So, hi, I'm Tomnomnom. If you know me, it's been a while. Hello. I make open source tools like Gron and Anu and Meg and FFF. Quite a few, it turns out. I went to count them and I lost count. I like questions, so have them ready. And I work for a company called Bishop Fox. I do sort of tooling, research and development type stuff. It means the slide deck is branded and in light mode, which is unusual for me, and also lacks the legally questionable use of stock photography that I copied off Google Image Search, which I usually use. But, can't have everything in life. So, crawling the web used to be kind of easy. Like links were links, marquees scrolled across the page, blink tags blinked at you, and there was under construction GIFs everywhere. But you just had these things, these links, pretty easy to parse. There's an href attribute that tells you that another page exists and how you can get to it. And then when JavaScript did arrive, it mostly just made the page look pretty, and we came up with this idea of, what do you call it, DHTML. That was the new thing. Everyone was writing books about dynamic HTML. But it was fine. It was pretty easy to deal with. And then about 2001, Microsoft gave us the pithily named gift of XML HTTP requests. And what that did for us was let JavaScript make HTTP requests for the first time and get responses. And that means we didn't have to reload the page to get new data in, or use a Java applet or a Flash applet or something like that. And fast forward a couple of decades, we now have a plethora of JavaScript frameworks to handle all this stuff. And what that really means for us is the web is now much harder to crawl. It's much harder to understand from a programmatic point of view, certainly. So I want a way to deal with this situation. And one of the ways you could deal with that is to use a headless browser. So something like Chrome, Firefox, whatever you like, running programmatically controlled, but without the GUI on the page. That works pretty well. But it's kind of resource intensive. If you've got a few thousand URLs you want to scan, running a few thousand instances of Chrome, if you've ever had 50 tabs open and viewed the memory usage, you'll know that that's going to be kind of tricky. It also has another sort of fundamental flaw doing this kind of dynamic analysis, that is to say, analyzing code that's currently running. And the problem with that is you want to find out about things that are actually running. So you're going to run a headless browser, you have to write a bunch of code to stimulate the page under test somehow, to click on buttons, open menus and all that kind of thing, to try and figure out all of the different bits of functionality and run all the different code paths in the several megabytes of JavaScript that was probably sent to the browser. That turns out to be kind of difficult to do. So you might consider doing static analysis instead, so analyzing code that's not running. And that means you can analyze everything. In theory, you can't do quite as good a job of it. You don't know about the data that's in memory, the value of variables, that kind of thing. So you might consider using regular expressions to do that. And there's a fairly well-known quote about that you might know about now you have two problems, you decide to use regular expressions, but let's take a look anyway. So this is a call to fetch, which is sort of the modern equivalent of XML HTTP request. There's a camera there. And the bit we want to pull out of it is this path here, /API/v2/guestbook. That's the bit that we want. And you think, well, that's pretty easy to deal with, right? So we'll use regular expressions. But you have to deal with the fact that there might be nested quotes or escaped quotes in there, that kind of thing. There's different kinds of quotes. There's 3 different kind of quotes you could use in JavaScript. For a start, there's differing white space, all that kind of thing. Every conceivable crazy thing, every crazy variation you can come up with probably exists somewhere on the internet. Because when you're working at scale, edge cases become common. You think, this only happens 0.01% of the time. If you're going to go and scan a million things, you're going to have dozens of cases of that thing. So, you come up with these regular expressions. So a few here. One only matches the single quotes, so you've got to do that. And then it doesn't deal with nested quotes. You've got to use back references and all that kind of thing. You finish all that piece of work. you now have several dozen really complicated regular expressions, like that one at the bottom. It's a little bit small to see. You don't need to see the detail of it. The point is it's a big, complicated thing that does one task. You've got to run that against many megabytes of JavaScript. It's going to take a long time. And even worse, now you have to maintain those horrible regular expressions. You don't really want to do that. And there's also the fact that, like, extracting the URLs and the paths so you can find new endpoints is nice. What would be a lot nicer is if you could also extract the context around them. We're talking about stimulating different code paths. That's true on the server side as well. That's what we're trying to do. Stimulate as many code paths as we can, because that increases our chances of finding vulnerabilities. But sometimes, like changing the HTTP method, changing a header, something like that, is going to change what code path gets hit. And if there is context around this path, API, v2 guestbook, it's a post method. We can see you've got to send content type application JSON. That's important information to know when manual testing, but even more important when trying to do automated testing, automated crawling. And also, the way we can solve this problem is by, in this case, using a thing called TreeSitter, which we'll look at in a sec. But I want to give a quick shout out to Lewis Arden and SEMGREP in particular, which are, SEMGREP is a fantastic tool. Lewis did a talk here at B-Sides back in 2018, same year I did my last talk, actually, on static analysis in JavaScript. And that gave me quite a bit of inspiration for how I built this thing. So, raw JavaScript code, it's kind of difficult to understand for humans, if we're honest. It's one of those languages where there's 12 different ways to do everything. And that means you will encounter all 12 ways every time. So TreeSitter parses JavaScript and dozens of other languages and produces this thing called a syntax tree. You might hear it called an abstract syntax tree or an AST. And TreeSitter itself is meant for tasks like syntax highlighting, and that means it's actually tolerant of minor errors, which makes it a really good pick for this kind of thing. And we're actually seeing the JSluice tool here for the first time on slide 8, because it can show us the tree, the syntax tree, or at least a textual representation of the syntax tree for a file. So we've got a really simple program, hello world, console.log, and underneath it you can see we run JSluice tree and the file name, and we get a textual description of the structure of that program in really quite minute detail, but in a way that makes it easy to write programs that do things with that program itself. So we can see there's a call expression, and on one side of it we have a member expression with the identifier console and the property identifier log, and then there's arguments, which is a string, hello world. We have type information for these things, and that means we can write code that deals with code much more easily. So the main thing I wrote this tool for was to extract URLs. And there's a Go package for this as well, which we'll have a really brief look at later, but for the most part, we're going to focus on the command line tool that comes with it. There's a few different modes. We've already seen one mode, the tree mode, but the other sort of the main mode, I think of it, is the URLs mode, where it extracts paths and URLs, endpoints that are found in the JavaScript file delivered with an application. And because it has access to this syntax tree, we don't have to rely on regular expressions to say, this thing looks like a path. We can rely on the context to say, this thing is a path. I know it is. Even if there's no slashes in it, no question marks, doesn't look like a path, you wouldn't find it with a regular expression. We know if you pass something to the fetch function in this position, it will be a path. It will be a URL. It will be used in that way. Same goes for XML HTTP request, document.location. jQueries.get and post and .ajax and a handful of other places that the tool also deals with. And it produces an output that looks like this. So it's JSON lines. You might want to pipe it to JQ to make it a little bit more easily formattable, but that means it's quite easy to write shell scripts that uses this tool for automation. So you can have something that fetches a bunch of files, run this against it, finds more URLs, goes off and fetches them, fuzzes them, whatever it is you want to do. And you can see we've extracted the URL, but also the method and the headers. And that's all down to the fact that we have that syntax tree available. That means that we can interrogate the context around that. We can do quite smart things, including something that would be really irritating to try and do with regular expressions, if not impossible. I'm not going to claim it's actually impossible because there's someone out there who's been writing Perl since 1980 who's now trying to prove me wrong. But probably. The problem with XML HTTP request, if you've never used it, is that all the bits of information we're interested in, like the path and the method and the headers and that kind of thing, are spread across multiple different function calls. They can appear in any order. We have one here that appears inside a conditional. It could be 10 lines apart. Right next to it, it could be 100 lines apart. We don't know. Writing a regular expression for that kind of thing is, like I say, probably impossible. But never say never. But because we have a syntax tree, we can do this really cool thing where we look for any call to something.open, where we have the method, and look for any instance of that where the string that's being passed as the first argument is a valid HTTP method. Once we find that node, as it were, in the syntax tree, we can climb back up to the parent nodes and look for any, what I would call a scope-defining node. So like a function declaration, or maybe just like the top-level program, something like that, that defines a scope in JavaScript. We take the object name, in this case XHR, and look for all other method calls on an object of that name within that scope. And that lets us find things like the set request header methods, and lets us output this structure on the right that includes all of the information that's relevant to that URL. The other thing you might notice there is we've got that xhr.open call. The path has a variable slapped in the middle of it. It's doing string concatenation. So another problem hit upon trying to use regular expressions for this stuff is this is a really common pattern, particularly in applications that are maybe 10 years old, something like that. And with a regular expression, that's really difficult. You might get the first part, the /API, but you're much less likely to get that query string part, $format equals JSON. And knowing about that query parameter might be the difference between finding a bug and not finding a bug. So you can see on the right, we actually replace the part where that variable would have gone with the EXPR, short for expression. And if you don't like that particular string, you can change it with the -- placeholder flag. But the point is, we turn that from something that is not parsable as a URL to something that's parsable as a URL. Might not be valid for that application with the string expr in there, but it tells a human, hey, this was a variable part of the URL, but we now know about all of the query string parameters and that kind of thing. So you might want to swap that out for, say, the word fuzz, for example, which is the keyword used by tools like Fuff. And you can run a word list against it and try and find API endpoints that way. You could do that in an automated fashion using this as input. The other thing JSluice can do is find secrets. Modern web apps talk to lots of APIs. They run in the cloud. And that means you need secrets for them. They also have modern JavaScript applications are incredibly complicated. And that means they have complicated build processes, which are often kind of opaque. You don't really know 100% which JavaScript files are going to be included in the source. Turns out it'd be really easy to accidentally include a bit of infrastructure code. Something that's got your AWS keys in it, or your GCP keys in it, or something like that. And AWS keys in particular are actually something that's kind of easy to find with regular expressions. They all have like a known prefix and a fairly well-known length, even though it's specified slightly differently if you look up the docs. But they're useless by themselves, AWS keys. You need an AWS key and a secret. And a lot of the time you'll find a key by itself, which is kind of disappointing when you see the result in your scanner and get excited briefly. But then, no secret. But again, because we have the syntax tree, if we find something that looks like an AWS key, we can climb the tree, find out if the parent node is an object, and look at the other parts of that object. Is there something in that looks like a secret? Unlike the AWS key, the secret doesn't have a particularly well-defined format. It's just some base 64 encoded junk. So if you have a regular expression for just the secret, you are going to get so many false positives it is not even worth bothering with. But because we have the context of the fact that we also found an AWS key in that same object, we can pull it out. We can put them into the results of JSluice with a well-defined name, key, and secret, so you can pipe that onto your automation that actually checks if the key is valid, for example. You can also see we have a context field in the results as well, with the entire object that those two fields were found in. And to a human tester in particular, that's super useful. AWS key and a secret, I've got those, maybe they work. Okay, what do I have access to? I don't know without the context. There might be an S3 bucket or some server URL or a reference to some resource in that object that's useful. And that's buried in somewhere in the middle of a multi-megabyte minified JavaScript file that crashes whatever text editor you're using, probably. Or at least it's hard to scroll to, right? But by extracting that context, we make it much easier for someone who's looking at dozens and dozens of cases every day to be able to, have the information that they need. There are, however, lots of different kinds of secrets out on the internet, it turns out. So JSluice has built-in matches for AWS, GCP, GitHub, and a couple of others. Like, not that many, really. And that's partly because it's an endless task. You will never finish. You could have 100 matches in there, and chances are the one target that you're looking at uses some obscure vendor I hadn't heard of. Or maybe they have their own particular pattern of secrets that you want to look out for. And because of that, JSluice supports custom patterns. And they use regular expressions. There's an example pattern file on the left. It's in a JSON format. And you can match against just string literals by themselves with a regex. And that, if nothing else, saves you from having to think about the quotes. Because every string literal in the source file is going to be extracted, have the quotes stripped off of it. It's going to be decoded properly. One of the things you might be aware of is JavaScript strings have about 5 different ways to escape things, \x, \u, and several other things. They're all dealt with for you. So you can write simple regular expressions that match against single strings. But you can also match against object keys, or both. Or in the bottom example, you can see we can match against an entire object. You can say, I'm looking for an object that has this key with a value that looks like this, and also has this key. So something that I've come across quite a few times in the past is uses of the Firebase cloud database, or whatever it's classified as, and the configuration sat there in a JavaScript file. And it's not necessarily an issue by itself, but knowing the key and the app ID and that kind of thing lets you easily check whether there are any improper configurations on that Firebase database. So being able to match an entire object, regardless of what order the keys are in or anything like that, turns out to be pretty useful. So we're using TreeSitter, as I mentioned. It's kind of a cool thing. And this is a mode I added to JSluice because I thought it would be useful for me. And then when I added a little bit more to it, I thought it turned out to be generally useful to people. So the query mode lets you run these things called TreeSitter queries. And it's its own little DSL, a domain-specific language for querying syntax trees. And if I'm honest, it gets kind of complicated. It's a little bit finicky to deal with, but if you get it just right, it can be really powerful. And you can use the tree mode that we saw earlier to help you write the queries as well, because you need to know about the types of the different nodes. So if you have some example code that you know is representative of the kind of thing you want to find, you can run the tree mode against it, see what the tree looks like, and use that to inform what queries you might write. We've got probably just about the most simple query we could write here. And the text is a little bit small, but it's the little dash q, and then there's brackets, object, brackets, and there's an @m. And the @m is just a thing that says, this is the bit I want to actually extract, is the objects. And that would let us extract all of the objects from the input JavaScript files, which is kind of useful, I suppose. But what's especially useful is because I sat down and read bits of the JavaScript spec and worked out all of the string encoding rules and all of the other bits and pieces. I've managed to make it so that you can take any JavaScript object, which is not where JSON is not compatible with a lot of the different things that JavaScript supports, like keys without quotes, a lot of the different escaping methods, single quotes, and so on, and turn it into valid JSON. And what that lets you do is do easy post-processing of the data that you've extracted from JavaScript files where the tool is expecting JSON. And we can see something here. There's kind of a fallback where not everything can be converted to JSON. In JavaScript, you can have a function as an element in an object. In that case, we turn the source code into a string, which is not ideal, I suppose, but it's the best thing we can do in this situation. But it means that you can pass this stuff off to JQ or your own personal written tool that has some really simple code to parse the JavaScript and look at the stuff that's in it. You can also use it to inform things like building word lists. So it might be that, for example, you're hacking someone's API and you need a good word list for all of the potential properties that are going to be in an object sent with an API request. That kind of thing can be really time-consuming to do, and generic word lists will not always help you because every target is going to have things that are specific to that don't exist in any of the common word lists. But just with a nice little one-liner, you can find all of the JavaScript files you've grabbed from somewhere, whether you've done that with wget or there's a tool called PageFetch, which I actually wrote and open sourced at my former employer, so look that one up, which uses headless Chrome to fetch all of the sub-resources and store them on disk. Let's run find for that. You can pipe those straight into JSluice. So as well as providing file names in the argument list, you can provide them as a series of one file name per line on the standard input as well. The output from that is JSON, so we can run that straight into JQ. We can turn each object using the toEntries function into an object that contains just the key and the value separately. So you can do things like extract the key very easily. Choose that .key. Time to sort, unique, to add counts, and then sort again numerically in reverse order. And we have a list of key names from all of the objects in that file, whether they were quoted or valid JSON or not. And they are ordered by how common they are. That kind of thing can really make or break the fuzzing of API endpoints in particular. So I mentioned JSluice is a command line tool, but also a package. The command line tool, I think, is what most people are probably going to use. But at least some people are going to be writing their own crawler, and they don't want to use a headless browser. They want to be able to extract URLs. Or maybe you just, you don't like the command line? Don't talk to me. But more generally, your needs might outstrip what I built into the command line tool. If you use the Go package directly, you can write your own matches where you get exposed to the full syntax tree. You have the full power of tree sitter at your disposal. You can run your own queries. You can run queries on subsets of nodes. So you can sort of filter things in that way. So you can say, give me all the objects, and then query just those objects, for example. And you can do custom matches. So if you can write the logic you need in Go, which you probably can. I'm not going to get into an argument about Turing completeness, but almost certainly if you need to do something, you need to call out to an external API or something. I wouldn't really recommend it because these functions are going to get run many, many times per file you run them against. But you can decode the strings, you can look at the prefixes and so on. All you've got to do is accept a JSluice node pointed to it and return a JSluice URL. And you can do that for secrets as well. So if you want to get serious, you might want to use the package. So to finish up then, one last one-liner. I seem to develop a reputation at some point for big fancy bash one-liners. And this one's kind of to address, I suppose it's kind of a shortcoming of the command line tool as it currently stands in a way, and a feature it might support natively in the future. You never know. But some of the most interesting things that you find in JavaScript are in JavaScript files. They're in inline JavaScript, particularly in slightly older web applications running, say, PHP, for example, where it's pretty commonplace to just echo things into the middle of the page. It's really common to see things echoed in the middle of JavaScript blocks, particularly things like environmental configuration, things that are going to change depending on what environment or what user you are and those kinds of things. They show up a lot. And that means we probably want to run JSluice against those inline bits of JavaScript as well. You can use a tool called HTMLQ, which is kind of like JQ, but for HTML. You write CSS selectors using it. So we'll find in this one-liner all files and we'll run the file command against them. And if you're not familiar, the file command gives you its best guess about what type of file it's looking at. We use grep to search for HTML documents only. Use cut to extract the file name from the beginning of the output. For each one of those lines, we'll read it into a variable called HTML file, and then we'll use JSluice secrets and a little bit of shell substitution to run HTMLQ against that particular file to get the script tags and extract the text from within them. And that lets us run the JSluice, the secrets mode in this case, but could be URLs, could be query, could be whatever you want. The tree mode if you really want, against all of the bits of inline JavaScript in this file. So that's all I've got for you. If you want to have a look at the tool, it just went public yesterday. It's at github.com/bishopfox/JSluice. Any questions? Yeah?
Yes, thank you so much for sharing this awesome tool.
You're welcome.
My question is, can we use this tool against obfuscated JSON?
Against what, sorry?
Obfuscated.
It depends on the level and type of obfuscation. Sort of the standard minification process, you'll be fine. If someone's gone to the effort of really obfuscating the JavaScript, it's not going to work, unfortunately. Because even when you have a syntax tree for some obfuscated JavaScript, still obfuscated. Especially if it's like, if you're with JSfuck, for example, where it's just braces. It's not going to work for that. One of the things that you can do, however, for certain cases, is if you use something like Chrome DP, for example, which is a Go package for driving headless Chrome, you can rely on the fact that you can do dynamic analysis to get a version of the obfuscated code to then do static analysis on. And it's a little bit convoluted, but it's very difficult to write general routines to deal with those kinds of situations, unfortunately. But my analysis of several gigabytes of JavaScript from several 100,000 sites is that obfuscated code is pretty rare, particularly for the kinds of situations that I come up against, which is legitimate companies who have a bug bounty program, for example, or in my case, Bishop Fox, who are customers. It's pretty unusual to come across that. Yep.
Have you thought about integrating it with a proxy and automatically running it against like automated tests?
I think I gave it some thought at some point. It's certainly something that you could do. You could maybe make a burp plugin for it or something like that and use it there. I've never written a burp plugin before, so don't quote me on that. But yeah, that's a really good idea. Hey. Yeah, so at the moment the output includes the file name. If you're doing the find thing that I did, you'll get a file descriptor, and that doesn't quite work. That needs a bit of improvement. I think we can probably get line number in there as well without too much trouble. There's a little bit of trickery I need to work out in terms of going from the syntax tree back to the source to figure out exactly what the line number is. But usually getting the file name is enough. Because if you have one file to deal with and you've got to go and grep through it manually, that's not bad when you filtered it down from hundreds of thousands already. Cool. I think we're about out of time. If you have more questions, feel free to come and grab me. Thank you very much.